So now we see another way of classifying the Raman process based on the spectral characteristics. So based on the spectral content or the spectral characteristics of the Raman process, we can classify the Raman process into different type of Raman process. One such is the band limited process. I think you might have heard this word band limiting, the meaning of band limiting. In the case of sampling theorem, we start with a signal that is band limited. Follow? So the same meaning again. So if you let x of t is a random process that is wide sense stationary. If you let the power spectral density of this process is Sxx of omega, then this will be equivalent to 0 in a particular interval, that is outside the interval omega 1 to omega 2. This power spectral density of the random process is 0. So if this condition is satisfied, the random process is said to be a band limited random process. Understood? X of t is wide sense stationary and the power spectral density. This is the power spectral density of the random process x of t is 0 outside a particular interval omega 1 to omega 2. Here we consider mod omega, that indicates for both positive and negative values of omega. So if you consider one simple example, that this is omega, this is the power spectral density. So let this is omega 1, this is omega 2. So minus omega 1, this is minus omega. See what this mod omega does not belongs to omega 1 to omega 2. That is outside that interval. That is this interval and in this interval and in this interval. In those intervals that is 0. In the remaining intervals from omega 1 to omega 2, it is non-zero. See here it does not belongs to omega 1 to omega 2. See, this interval is belong to omega 1 to omega 2. So outside that interval, that is mod omega doesn't belong to the interval omega 1 to omega 2. Outside that interval, this power spectral density is 0. That is from 0 to omega 1 it is 0, for omega 2 to infinity is 0, and minus omega 1 to 0 it is 0, and minus infinity to minus omega 2 it is 0. So this is non-zero over a finite band of frequencies. Therefore, here I am selecting some arbitrary shape. The shape need not be same. Just I selected some arbitrary shape. We may consider this interval, or the difference between omega 1 and omega 2 can be considered as some W. So what we call that W is a bandwidth. So here this W is a. So how can you define the bandwidth? The range of positive values of frequency for which the spectrum is non-zero is called as the bandwidth of the signal. The same is applicable to the process also. Why? Because this random process is the random signal, is it? I think you might have studied this concept in the case of deterministic signals. What is the bandwidth of the signal? It's the range of positive values for which the spectrum is non-zero. See, the range of positive values of frequency for which the spectrum is non-zero. In this interval, the spectrum is non-zero. So these are the range of positive frequencies for which the spectrum is non-zero, is called as the bandwidth of the signal. Same definition applicable to the random signal also. Understood this? So that is the meaning of the band limited process. The process is said to be band limited if the power spectral density is non-zero or a finite band of frequencies. Take for example, this process. For a particular process, the power spectral density is given like this. Let this is minus omega 1 and this is minus omega 2, this may be 0, this is omega 1, this is omega 2. So if you observe this particular process, is it band limited process? It's not band limited. Why? Because the spectrum is non-zero for the entire interval of frequency. See, it is non-zero. It is not becoming zero here. Or otherwise, if you consider a finite band of frequencies, this is non-zero over that interval. But whatever the other interval other than that finite band, in that interval also it is non-zero. So therefore, this is not a band limited process. So here, if you let this center frequency is some omega naught, this is minus omega naught. That is, the spectrum is centered at omega naught and minus omega. So here also, if you let this is omega naught, this may be. See, if this omega 1 equivalent to 0, then this will start here and this will start here. So therefore, the spectrum is centered at omega equivalent to 0. So then the process is said to be a low pass process. Followed? With the power spectrum is centered about the 0, about the origin of omega equivalent to 0. And the process is said to be a low pass process. That is, for a low pass process, the spectrum looks like this. Here spectrum is the power spectrum. So we are discussing the power spectrum of the process. Take for example, see, all the shapes that I selected are arbitrary shapes. Just I selected some arbitrary shapes. Why? Because we don't know what is this x of t exactly. This is the power spectrum or the power spectral density of the process, and the process is said to be a low pass process. So this is an example of a low pass process. Here, this process is also called as the band pass process. That is, the spectrum of the band pass process is non-zero for a particular interval of frequency, and that is centered at frequency omega naught. Normally here this omega naught, in this case, in the case of band pass process, this omega naught is chosen in such a way that omega naught is very greater than when compared to the W. So what is this W? This W can be considered as this bandwidth by neglecting these amplitudes. That is, by assuming this is almost that is after below omega 1 and greater than omega 2, the power is very less, it is negligible. Then we can assume this as the W, or otherwise let it be or W simply. The difference between omega 1 and omega 2 is W. If this omega naught is very greater than W, then the process is said to be band pass process. So these definitions are similar to that of the definitions of band limited signal, band pass signal, low pass signal. So now we see some important properties of this particular band pass process. So if you let x of t and y of t are two jointly wide sense stationary process with zero mean. X of t and y of t are jointly wide sense stationary with zero mean. Then we can define a new process called u of t as x of t cos omega naught t plus y of t sin omega. So such process exists in the communication systems. Normally we take a high frequency carrier, this is called the high frequency carrier signal or simply carrier. The parameters of this particular carrier are modified in accordance with the information bearing signal. So that process is called as modulation. So in that context we encounter the band pass signal. If you let this x of t and y of t are low pass. Both are low pass process. Then we can obtain a band pass process by simply multiplying each low pass process with a cosine function with frequency omega naught. We select this omega naught in such a way that this omega naught is very greater than the highest frequency that present in x of t and the highest frequency that present in y of t. If you let the highest frequency that present in x is fx and the highest frequency that present in y of t is y, omega x, omega y, because we are using omega here, either way can write, because both are the frequency. Select this omega naught in such a way that omega naught is very greater than omega x and omega naught is very greater than omega y. So the process u of t obtained by multiplying the low pass process x of t with cos omega naught t and then y of t with sin omega naught t, then the sum of those two, x of t cos omega naught t plus y of t sin omega naught t, is called as the band pass process. So if you know two low pass processes, we can obtain a band pass process. So here this representation is the band pass representation. So why we are calling it as band pass? See, if you multiply a function x of t with cos omega naught t, the spectrum of the x of t is shifted to omega naught. Similarly, if you multiply y of t with sin omega naught t, the spectrum is shifted to omega naught. I think you might have studied the modulation property of the Fourier transform. This is also called as frequency shifting property of the Fourier transform. So, according to the frequency shifting property of the Fourier transform, if you multiply a signal with sine, whether sine or cosine, the spectrum of the signal is shifted to omega naught. Why? Because if you let the Fourier transform of x of t is x of omega, and the Fourier transform of x of t cos omega naught t will be 1 by 2 x of omega minus omega naught plus x of omega plus. Otherwise, you can write x of f minus f naught plus x of f plus f. Either way can. So this indicates the spectrum x of, if you let x of omega or x of t is low pass. X of t is low pass, where the spectrum is centered at omega equivalent to 0. Now, when you multiply this x of t with cos omega naught t, the spectrum is shifted to omega naught. Now it is centered at omega. So therefore, this particular x of t cos omega naught t is the band pass. Is a band pass signal. See, x of t is a low pass signal. Then x of t cos omega naught is called as a band pass. In the same manner, if x of t and y of t are jointly Weier's and stationary random processes with zero mean, and x of t, y of t are also low pass processes, then u of t equivalent to x of t cos omega naught t plus y of t sin omega naught t is called as the band pass process. Understood the difference between the low pass process and the band pass process? Here x of t and y of t are given, we obtain the band pass process. For example, u of t is given. Can we find x of t and y of t? So definitely there is some method. We represented u of t in terms of x of t and y of t. Definitely there may be some relation exists. Okay, x of t in terms of u of t, y of t in terms of t of t. So for that purpose we use the concept of Hilbert transform. So here, if you let u cap of t is the Hilbert transform of u of t, then we can define a new process z of t that equivalent to u of t plus j times u cap f. I studied Hilbert transformation. So u cap of t is the Hilbert transform of u of t. Then this particular new process z of t is equivalent to u of t plus j times u cap of t. Then you can write this x of t as real part of z of t into e power j omega naught t, and y of t is equivalent to minus times imaginary part of z of t e power j omega. We know z of t. See, u of t is known to us. If you know u of t, we can find its Hilbert transform. What is Hilbert transform? So u cap of t is equivalent to integral minus infinity to plus infinity u of tau divided by t minus tau d tau. That is, u of t is u of t convolution with 1 by phi t. So if u of t is known to us, we can find u cap of t. So therefore, we can evaluate z of t. So if you know z of t, multiply with e power j omega naught t, and take the real part of that, you will get low pass signal x of t, and the minus of imaginary part of this term is a low pass signal phi of t, or low pass process phi of t. So here in this slide, so this particular term, this term is called the in-phase component. In-phase component of u of t, and this term is called as the quadrature component. X of t cos omega naught t is called as the in-phase component of the process u of t, and y of t sin omega naught is called as the quadrature component of the process u of t. So therefore, this band pass process is represented in terms of its in-phase component and the quadrature component. Why? Because the phase difference between cos omega naught t and sin omega naught t is pi by 2. So here there is some phase difference between this term and this term. Okay, that's why it is called the in-phase, and this is a quadrature phase. Similarly, we have another process called the narrowband process. So if you like, this is the power spectrum of a particular process x of t. That x of t is a process, and its power spectrum is this. This is omega naught, omega 2 plus omega 1. And this is minus omega naught, minus omega 1, minus omega 2. So we call this difference as the bandwidth W. So what type of process is this? It's a band limited process. If you let this W is very, very small compared to omega naught. If W is very, very small compared to W naught, omega naught, omega 1 and omega 2 come close to omega naught. Then the plot may look like this. This will become omega. This is minus 1. Now what is this? This difference is the W. That is, the bandwidth is very, very small compared to the omega naught. What do you mean by bandwidth here? It's a W2 minus W1. When this W become very, very small, if W1 come close to omega naught, W2 also come close to omega. Both come very close to omega naught, then the width is small, that is W is very, very small. Then the process is said to be a narrow band process.